Hello everyone, welcome to lecture 12. In this week, we're going to talk about the integration. So specifically integration by substitution. How do we calculate the integration of expression by substituting an expression, another expression, right? So, and also integration by parts. What do you mean by that? And then later I'll talk about the definite integral and its properties, along with area under the curve, or between two curves. All right, so let's get started. Okay, so first we have, so this is what we have. So u is expressed as a function of f of x. Then naturally we know that u prime, which is the derivative of u with respect to x, can be expressed as the derivative function of f prime of x, and can also be expressed as du over dx, right? So that's our definition of the derivative. So moving these parts here, then we have this expression here. So this is expressed as du is expressed as a function of the derivative multiplied the differential of x, right? So this is just shuffling the terms. Now, what this means that if there's an expression, so if u is expression of x, then we can just take the derivative, and then we can express du as a function of dx, right? So this is in the derivative space. So let's look at one example to see how this can be put in practice. Okay, so we'll look at let's look at this first example. So in this case, we are looking at something which is in the parentheses. This is raised to the power of 6, and then another term. So these are two terms multiplied together, and we want to take their to calculate our integration. So integration is with respect to dx. Now, what this means is that we actually have two terms to worry about, and if we had to have just one term, right? If I just one term in the integrand, so this is again integrand. Right, so this is integrand. So inside integrand, if I just one term, then it will be much easier to calculate, right? So this portion itself seems to be related to the second term, which is 3, right? If we take the first derivative, if we take the first derivative of the first term, right? In this term, then 3x plus 4, then the derivative is just 3 itself, right? So these two are related, and this gives us a hint. If we can just express u as 3x plus 4, then we have du is equal to 3 dx, right? So if you just take the derivative of both sides, and then we have this relationship. Now this helps us to express the original expression. So let me just use this. So this original expression can be expressed as integral, like u raised to the power of 6, right? And then what we have is that this 3 times dx is just equal to du, right? Just to be du. So at this stage, this is what we know how to calculate, right? Just raised to the power of 7 divided by 7, right? Always remember to plug back, see if they equal to each other, and then plus c is a constant, right? So constant, and we can just plug back the definition of u to help us get 3x plus 4 to the 7th power divided by 7, then plus constant c. So this is how we can calculate, and this is called using substitution technique to calculate the integration of two terms multiplied together, right? Okay, so again, always remember to check your answer backwards. For example, if we take this guy derivative, that should be identically equal to this portion, right? Okay, so let's move on. Additional substitution technique. So basically what this means is that we actually want to express, so the integrants must be expressed entirely in terms of u and du, right? So u and du. So this is just to facilitate the analysis and the integration operation. And they may sometimes require you to change the integrand a bit to reshuffle or re-express the term so that we can actually do this to totally express the integrand as a function of u and du, right? So, and if it does not, then we need to change a bit. So let's look at the first example. So in the first example, we have 1 over something, right? This something looks a bit complex, but it's just a first order polynomial function. It's a first order in X. Now, so this requires a bit of exploration, but if we want to take u equals to 4x plus 7, right? So this will just give us 1 over u, right? But what happens to dx? So we can take the derivative of both sides, right? So this can be du equals to 4 times dx, right? So if we can construct, so if we can have something that is 4 times dx, then we can just plug in the definition of du, and then we just replace x, right? So now what this means is that this will become u, so just so 1 over u, I'm just plugging the definition of the function and to multiply dx, right? So now I want to construct something 4 times dx. What do I do? So I would still write the same thing, and it's gonna be multiply 1 over 4 du, right? So because I'm just re-expressing this as dx equal to 1 over 4 du, right? So I'm just dividing 4 on both sides. So this is what I have. And because this is the constant, I can move it outside. So what I have is 1 over u du, right? So this continue. We just want to take the integration of this portion. And based on the property we discussed earlier, that this is a function. This is a derivative of lowering absolute value of u plus a constant c, right? So to see why this is the case, then we can just plug back in and the derivative of this one, and then see it's actually equal to 1 over u, provided that u is actually so this portion should be positive. Then that's why we have the modulus here. And at this stage, we can just plug in the definition of u. So it's going to be ln 4x plus 7 and plus c. C is any constant. All right, so this is what we mean by doing a bit of change on the expression, so that now we actually have this extra 1 over 4 here. Then that's why we need to have to change a bit, so that it's actually can be something we can plug in and to replace x, and then you use that to express the original integration in terms of the new notation u, right? Okay, so integration by parts. Now, this means that we actually want to use what we know and then derive some property from that. Right? So what do we mean by that? Now remember that we have two functions. So assume we have two functions f of x multiply, right? So this is multiply g of x. Now these are the two functions. So if we want to take the derivative of these results, so derivative with respect to dx, right? So this is the whole chunk. We want to take the derivative. We want to take the derivative of this expression with respect to dx. Now, based on the product rule, we would differentiate first one, multiply the second one, and then plus the second one, and then multiply the first one derivative, right? So this is the product rule we covered earlier. Now, if we integrate both sides, right? If we integrate both sides, then we have what we have here is that we're gonna have so this is so let me see. We have integral f of x g prime x. So this is the integration of these parts of this part, and then integral. Okay, so let me maybe just rest on the direct result first. So if we just take the integration of both parts, so we want to take integral of these parts with respect to the x, right? So they will do the same for everybody. So this is our inner side, and we just take the integration of each portion, right? So this gives us, so we're going to take the derivative first and then take the integration. So it's gonna be itself, right? It's gonna be itself. And remember, the constants, they will all cancel each other out, right? So and then the on the right side we have so this is gonna be the integral of f prime of x gx, right? And then dx, just removing the parentheses, the big brackets, and then plus fx g prime x dx, right? So this is what we have. Now, reshuffling the terms, we have f of x g prime x. Now I'm just moving this term as a standalone, which will be equal to fx gx minus, it's going to be right, gx first, prime x dx, right? So I'm just reshuffling the terms. So what this means is that if I want to calculate the integration of this guy, right? So this is one function and multiply the derivative of another function, then this is going to be, so the result can be calculated as these two original functions multiplied together, then minus the other way, the other combination, which is that's the raw function of g multiplied by the derivative function of x, right? So now this will be very useful when, for example, it's very difficult to calculate this directly, right? So now I can just calculate based on the right portion. So now if we just do a bit of abstraction by expressing the g of x as a function of v, right? So v is equal to g of x, then u is equal to f of x, right? So now this will give us dv equals to g of x dx, then du will be f prime of x dx, right? Just take the derivative of both sides. Now, based on this, now we can have the integral of u and dv, right? So that was the case because now this is just equal to dv, right? So we just express as a dv. We just move the g prime of x inside, and then as an entity, as a whole, and then we can express as a dv. This will be equal to u times v minus the other way around, which is v and du. So why is it du? Because this portion is solves the definition of du, right? So this is what we mean by integration by parts, because we literally, so originally we calculate the dv, right? And then now we can just worry about du. So this will be helpful in certain cases to calculate the integration, right? And specifically in what sense? So that's why we look at an example. So based on this formula we have, now the expectation, the general expectation is that this new integral, so we have a new integral here, this should not be more complicated than the original integral, right? So we hope that this new integral will be simpler than the original integral, so that it's easier to calculate, right? So of course, there's this question, if there are two terms, if one term, two term, and then the integral of both terms, so which one should I set to u, and which one should I set to v, right? So so this is a question we have, and there are some rules of thumb. So for example, if it involves both a power function and the exponential function, then we typically let the exponential function to go to v, right? So to be the differential we want to have in the integral expression. Now the reason is because that it's actually d to the d of ex is going to be ex dx, right? So because calculating the differentiation of this term is actually easy, right? So it's easy. So we usually let the exponential parts to go to the v, which is the part of differential in the original integral. Now, if we have these two terms, then we would actually let this portion, this power function, go to v, the function v. And the reason is exactly this is what we know how to calculate, right, in terms of the integral. But this is a bit difficult to calculate, right? So that's the reason why. So whatever function that goes into v, it should be simpler. So this should be simpler. Okay. So now let's look at one example to see how this works. So here we have one example on the two functions, x and e to the power of x. So based on our previous analysis, and we can actually consider let's e go to function v, right? So basically v is equal to ex, right? Basically, now what this also means is that dv is equal to ex dx, right? So ex dx. Now, naturally, u will let it to be x. So now original expression can be expressed as integral of u and just dv, right? So you just dv. And this is exactly because now this portion is equal to dv. Okay. So now this is where we use this formula, integration by parts, so that we have uv minus v du, right, integral. Okay, so just write properly v du. Okay, so and on this step, we can now safely plug in. So we have x multiplied e to the power of x minus integral. This is going to be ex dx, right? So, and this is what we know how to calculate. So this portion is just going to be self ex plus any constant c, right? So if you take the integration of both this portion, then it's going to be this one. So, and then we just plug it back in. To solve for the integration of this expression. So, and also remember to plug back your answer so that it's actually equal to the original integrand. All right. Now let's switch gear and to look at the last portion, which is definite integral. So there's quite some information, but hopefully you follow the intuition here. So the key idea concerns the problem of how to calculate the area under this curve, right? So this is what we call a definite integral because there's a definite starting point and end point. So what is the shaded area, right? How much is it? Now there are different approaches to calculate. So the approach, so that for example, we have the left rectangles and right rectangles. So how do they come about? Right. So the calculation goes like this. So if we divide the x-axis to intervals, right, of equal space, right? So these are the integrals. We have four. So 1, 2, 3, 4, four equally spaced rectangles, and we want to use these rectangles and add them up together to approximate, right? So this is very important to approximate the area under the curve. Now, so this is what we want to do. And if we use something like this, which you call left rectangles, then our calculations is like this. So basically, we would calculate the area of this first one, right? So first one is just this guy here. So we get the height of the first rectangle by the left, so the joint points of the rectangle with the curve, and then this is the height. So f, this is f of 1, right? If you just plug in the value of x equal to 1, then we can get the value. So this is x equal to 2, f of 3, f of 4, right? So these are the heights of the rectangles we have, and then we just multiply and it gets area. So this is second area, which is this one. The area, this one, and the fourth area, which is this one, right? So we can just plug in the evaluation and calculate one value. So this is what we call approximation using the left triangles. Right. So now correspondingly, we can actually use the right triangle, which is this graph. Yeah, so we have F2 here, now F3, F4, and F5. So of course, graphically you can know that this actually we're calculating more than the area under the curve, right? So this case is less than because we have this empty space here, right? So which actually did not account for. Now using the right triangle, we have this surplus, right? It's actually we're over counting, right? But the calculation works similarly. So we first get the height of the first triangle multiplied by the width, and then the area of the first rectangle. This is second rectangle, third and the fourth add together. So this is of course this value is more than this value because this is how we choose the rectangles, right? So both actually do not get as exact the area under the curve, but they serve as approximation. Right? So this left triangle or right triangle, they actually serve as approximation. And there's this theorem which is called area bounds for the approximation. So how good is the approximation? And we talk about error. We're taking the absolute error, right? So this is absolute error. So this is absolute error on the approximation. So this is of course so using the left triangle, we actually short of the empty spaces, right? So and using the right triangle, we're actually overcounting using the extra empty spaces here. So the error, if we compare it with the true error under the curve, right? This true error under the curve, then the error can be bounded by this expression, right? So by this expression, now what is this? So this is a literal interpretation of the additional sum of additional all the empty blocks. Right? So what do you mean by empty blocks? So if you look at this graph, right? So this is actually the sum of all the individual white box rectangles. So if we just indicate here, so this is the white boxes. So to why is that case? So each so for example, okay, so this is literally shifting the white boxes here, right? So and then we stack them together, and then we form this triangle. So this rectangle. So this rectangle, we have the height, which is the endpoints minus the starting points in terms of f, and then the interval here, and then we just get the area for this rectangle. So this rectangle represents the maximum bound, right? The maximum error we can make on the approximation. So again, we're using this quantity to approximate the area, and we're going to have some error, right? Because it's not an exact approximation. So the approximation error is actually bounded by this one. So now what is this? Right? So what is the rectangles here? So these rectangles actually represents the case that we're actually adding all these individual rectangles together, stacking them up, and then sum up, and then it gets us this value. So this is the value of all the little rectangles added together, and that's exactly because we're actually either in the left triangle case, we're actually not considering this portion, right? So this is using the left triangle, left rectangle. This is what the error will make, right? If we sum together all this, and using the right triangle, this is the error we make, right? Because we are over counting. So in either case, we are making error, and this error, we can just bound this by the sum of all these little rectangles. Okay, so this is just some analysis on how good the approximation is. So in either case, because we're using just 4 rectangles, so if the number of rectangles n, right, goes to infinity, then their approximation will be exact, right? So there will be conversion to the same value, right? So same real number. So both will be a good approximation, and then there will be a same number, which is the true area under the curve, right? So that also means that graphically, the width of each rectangle becomes infinitely small, right? Go to the limits, they'll be infinitely small, then just directly summing all the little rectangles to get the area under the curve. All right, so let's look at look at it in more depth. So we have different summations. So the left sum is something we can abstract. This is for example, this is our delta x, which is the interval of the rectangles, and then we have different points here. So this is using the left sum. We have fx 0, 1. This is how we can compress the summation, right? So all the different terms here, and then the same interval sum together. Now, right sum, we're just shifting 1 unit on the right, and then we have fxk, right? So this is not so using the right point to get the height of the rectangle. Now, what's a Riemann sum? Means that instead of using either the left point or the right point, right? So what do I mean by left point, right point? So the height of the rectangle, we're using either this point or this point, right? So meaning we're either if we use this point, then it's going to be this one to approximate. With this point, it can be this one to approximate, right? However, we can think about using any point in between. So if we use this point, then we're actually using this triangle, this rectangle to approximate the area, right, to do the summation. So this is what Riemann sum is about. So Riemann sum is actually using any point in the middle, right, to calculate the area under the curve. Okay, so for example, graphically, if we look at here, we choose this point, and this point is in between here and here, right? And this point is between here and here. So any point in between the interval, the starting and the point of an interval will be fine. And it's actually something that we can calculate as well, right? So here we have an example problem. So let's see k, which is the heights, the point that calculates the height of each rectangle, be the midpoint, right? So midpoint, and then how do we calculate it? So basically, we just need to find from the interval. For this interval, 1 to 5. I will have 1, 5. I will have 2, 1, 2, 3, 4, 5. And midpoint means that we're going to take 1.5, right? 2.5, 3.5, 4.5. So this is our points, and we use this to calculate, for example, this is the height of this one, of this point with the height of the second midpoint, etc. And then we can just plug in the formula to calculate the area under the curve. All right, so this is what Riemann sum does. Okay, so last point about definite integral is that it actually does the geometric interpretation. So the correspondence of this expression is graphically, it can be expressed as the sum of negative a plus b, right? So why is it negative? That's because it's actually we have the sort of the directionality of the area as well, right? So it's a signed area, the sum, cumulative sum of signed area, right, between the graph and the x-axis, right? So that means that when we actually calculate, we need to actually take into account the sign of the area as well. All right, so and we have last point, which is just talking about the approximation. So what this says is that when n goes to infinity, right? So this summation of little rectangles will just be equal to the original area on the curve, right? So this is all that's talking about. So it means that the quality of the approximation will be better and better if the rectangles are being smaller and smaller in width, right? So okay, so that's it for this class, and thanks for watching.